Okay, yeah, thank you very much. Yeah, Ewan Jures. I'm a principal engineer at WSP Parsons Brinkhoff. My team specialises in district heating design with consultant engineers and low and zero carbon energy solutions for communities. So, moving on to the right. So the talk I'm going to give is titled "Heat Pump District Heating: An Integrated Design Approach," and I'm going to, there's two parts to this really. First is about where heat pumps can be used with district heating, and the second is our approach to design for an integrated design approach for a retrofit district heating project. So I'll look at quite a lot of this will be about retrofit because although there is some new build, about 99% of our properties are still existing properties and they'll be around for a long time, and we need to find a solution for these properties that delivers lower cost and lower carbon heating. So when we do a study, such as a feasibility study for a district heating scheme, we often look at a variety of heat sources, but all of which do have their constraints. And typically there's some summary of the constraints we experience in the slide here. For biomass schemes, frequently we can't get access for deliveries. We get problems with air quality concerns, especially in urban areas where you've got air quality management areas. And just the size of a flue stack can be a problem getting through planning. And that's especially a problem if you've got an urban area where you've got quite a lot of tall buildings around. You may have to have a flue stack that's as high as the tallest building you've got there. Gas engine combined heat and power obviously only works if you've got a gas supply. And the other problem with in a residential scheme, you can't make use of the electricity from the gas engine at directly for consumers, so it has to be exported, and you get a low export value, which can impact the scheme economics. Ground source heat pumps can be used, but there are sometimes limitations where you haven't got enough ground available for the borehole array, and also the boreholes represent a big capital cost. And water source heat pumps, if you haven't got a suitable body of water near where you need your heating, they don't help. So with working with Star Renewables, we identified that there was a potential for a technology to improve their air source heat pump and use air source for district heating. Air source doesn't have any of these constraints, and in the UK it's particularly suitable because actually the weather, the climate in the UK is actually quite mild. So it's illustrated in this graph here. This is a temperature profile by hour of the year, or number of hours per year, and the temperature that's reached in Glasgow. It's important, the focus on when you're doing heating design is usually about designing for the design day, which is in Glasgow it's defined as a temperature of minus 3.9 degrees. So that's right down on this end of the graph, and you can actually see that you've got the heating demand through the year is any time when the ambient temperature is less than 15, and actually most of the time it's actually between 15 and about 5 degrees. You're most of the time you're working in that zone, although we designed for the extreme conditions. By taking that into consideration, the viability of an air source heat pump becomes much more attractive. So sort of go on to the actual project we've been looking at to illustrate the case. So this is a project that started off with Glasgow Housing Association, and it's an estate called Hill Park Drive. It's in a 350 home social housing estate in the south of Glasgow. Consists of the aerial view there. You can see along the top there are 5 multi-storey blocks. They're 8-storey blocks in there, and the 2 longer units down the side of the estate. So these 2 are 6-storey dwellings. They're all built in the 1970s. They're all fitted with electric storage heating. It's an area of high social deprivation and fuel poverty. And a housing association doesn't want to put gas heating into these buildings, partly because of the high-rise issues and partly because of the issues with servicing and maintaining gas boilers in these properties. So we did a first feasibility study for them, looked at biomass versus heat pump options. Biomass is quite tricky on the site because of access constraints and the need for a flue. The site is on top of a hill, nowhere near any watercourses, and there wasn't enough space for a borehole arranged for a ground source heat pump. So that's why we worked with Star Renewables to actually progress to a second detailed feasibility study and develop the air source heat pump concept for district heating alongside the actual design for the district heating system itself. So because there are some limitations with air source heat pumps or heat pumps generally, we needed to take a very integrated design approach, and the sort of key considerations we've taken into account with the design of the district heating system. Firstly, how much control do you have of the scheme specification overall? Well, fortunately with this one, we're dealing with one type of property. We're replacing all the electric heating systems, so we had full control from the energy centre through all the underground network, the distribution network, right down to the customer's heating system. We had full control of the design specification for the system. If we hadn't, if there had been existing heating systems we'd had to connect up to, that would have been a further constraint. But fortunately, in this case, we didn't have that issue. So therefore, we could design the whole system to suit the heat pump. So the heat source itself, as I say, we're looking at an air source heat pump because of it fits with the other site constraints. The heat source itself, it's got limitations in terms of the temperature it can deliver. We're not up at the multi-megawatt scale, so we're constrained to working at a flow temperature around 60 to 65 degrees. It was necessary to work closely with Star to understand how a heat pump would operate, given the weather profile, the ambient temperatures, how its efficiency and capacity would vary with the variance in ambient temperatures, and model that into the design of the network. Moving on, looking at the customer requirements, temperature for the hot water, that's pretty constant all the year round. We designed with an instantaneous hot water system, that provides maximum 48 degrees, which is compliant with the building regulations, and provides a 15 litre per minute shower capability. And temperature for the space heating was particularly critical. It's very much driven by the heat emitters. Because of retrofitting, it had to be standard wall-hung radiators. We couldn't do underfloor heating. Physical constraints, the actual sizes of the rooms limited how big the radiators could be. However, the heat pump could only deliver 60 degrees to the customers. However, by considering that the design day conditions for heating design only occur for a few hours a year, actually the requirements are a lot less for the rest of the year. We could relax the size of the radiators a bit and use some top-up heat for the few hours a year that was necessary. That allowed us to use the heat pump to deliver most of the heat throughout the year. And that's shown by this chart here. This is the predicted network flow temperature throughout the year. The heat pump is basically aiming to set on and deliver at 60 degrees, so the heat pump delivers all the heat up to the sort of constant 60 degree mark there. Where you've got the spikes in flow temperature, that's where additional heating is required, and the system responds and puts on gas boilers to supplement for a few hours at a time to boost the temperature, and that makes sure that there's enough heat through the whole system to deliver peak heat requirements. So this led to the conclusion that control of the whole system specification was vital. You've got to get the property internals right, ensure the correct commissioning. Heat interface units have got to be correctly designed to cope with the low and variable temperatures and low temperature distribution network. That means we can use polymer pipe, which is cheaper and easier to install and lower losses. But the key message for this is that graph there shows what the carbon saving can be. The blue line is electricity grid intensity going forward through time. The red line is gas boiler carbon emissions. The green line is where we can get to with heat pump. And as grid emissions, it already starts off low, but as grid emissions fall, it falls even faster. And that's a key message, I think. And that's why heat pumps have got so many useful applications. So, yeah, that's a conclusion. It's a useful technology. The air source heat pump overcomes a lot of site constraints, but we've got to get the whole system design specification matched to it. Thank you.